Welcome to the afternoon session of today. And our first speaker is going to be Simon Cornish. He's going to tell us about Ultracold reducing molecules in Magic-Wavelength tracks, a platform for quantum simulation.
So thank you very much, Anna Maria, and also thank you to the organizers for the invitation to speak here. It's my first time in India, and I'm very excited to be here. So as Anna Maria says, I'm going to tell you a little bit about some molecules and how they could potentially be used for quantum simulation. So because perhaps molecules are not so familiar, I thought I'd start with some high-level motivation. These are the four areas that I think molecules are important and can contribute. So traditionally, molecules have been very important in the area of precision measurement. You can do fundamental tests of physics in a molecule that are with far greater sensitivity than is possible in an atom. Our field has also studied ultracold chemistry. So this is an image from Kangwen Ni's lab in Harvard, where they study collisions of KRB molecules, and this is a reactive collision. And so they can probe fundamental quantum chemistry processes in this ultracold domain. And of course, molecules are one of the platforms that has been proposed and it's now becoming a reality for the study of quantum computation or quantum simulation. And I'll tell you more about these areas as the talk goes on. So why so much diversity and why do we like molecules? Well, it simply comes down to these extra degrees of freedom even in a simple diatomic molecule. You get this vibrational degree of freedom and the rotational degree of freedom. And altogether, this spans a huge energy scale. So you really can access transitions across all domains of the electromagnetic spectrum. So today I'm going to focus on this rotational degree of freedom. That's what a lot of the proposals make use of. And if you're not familiar, this forms this beautiful ladder of rotational states. So the energies are given by multiples of the rotational quantum number n multiplied by this rotational constant b. Okay, and so this is an anharmonic ladder. So the separation is 2b, 4b, 6b, and so on. And these states are all very long-lived. So the transitions between them are typically in the microwave domain, and they're allowed because our molecule can have a dipole moment in the molecular frame. So this is an electric dipole allowed transition between these neighboring states in the molecule. So we can use that. I mean, I've illustrated here picking two levels to encode a spin path system. But really, I want to emphasize that all of these states exist. They're all there. They're all long-lived, and so I think the molecule is much richer than a simple two-level system. And one area that we're becoming interested in is actually using these many levels to encode what's called a synthetic dimension. So effectively take these discrete energy levels and map them onto a synthetic lattice, for example. And here the tunneling is now controlled by the microwave fields that couple together these states. And of course, you can reconfigure the geometry of your synthetic lattice very easily by just changing the microwave field. And I'll not say any more about this because Adash is going to give a talk later in this session that will tell us about some of the experiments we've been doing on this topic. The other ingredient, of course, that attracts people to molecules is dipole-dipole interactions. And this takes one of several flavors. I mean, the simplest one to understand is, well, first of all, perhaps I should explain the electric dipole in a polar molecule, a diatomic molecule, points along the internuclear axis. And these wave functions tell you about the orientation of the internuclear axis. And so what you can see quite simply is in the lab frame, the dipole moment is actually 0. So we have to do something to engineer these interactions. The simplest way is to apply an electric field that mixes opposite parity states and produces a lab frame dipole moment, static dipole, which is proportional to the size of the electric field. Also, we naturally get spin exchange interactions. So if you prepare a molecule in this down and up state and they next to one another, they can exchange this excitation through the dipolar coupling. So the natural ingredient is spin exchange. And so these interactions together give this well-known XXZ Hamiltonian of quantum magnetism. Okay? And this is the basis then for engineering entanglement or for doing quantum simulation. So the idea is you prepare arrays of molecules and use this interaction to engineer the Hamiltonian you're interested in. The challenge, I would say, that the field has faced for a long time is actually getting really good quantum control of both the internal and external degrees of freedom of molecules. And I hope what I can show you today is that now the field has reached a point where this is achieved, and we are starting to explore some of these applications of molecules. Just to highlight, you may hear people say the strong dipolar interactions in molecules. I want to point out that the energy scale is of order of kilohertz. Actually, you'll see it can be a lot less. And one of the big challenges that I'll talk about today is actually accessing this in the presence of the optical trapping that we use to create these arrays, which typically produces energy shifts of hundreds of kilohertz. And so we really have to balance these shifts very carefully in order to access this dipolar interaction. Yes, that Ardash will talk a little bit about that, but today I will probably just talk about two levels, but absolutely, I think that is the selling point of molecules, that you have these long-lived states, a whole array of them. Yeah. Okay, so what I'm going to tell you about is actually how we assemble individual molecules in optical tweezers, and then how we can unlock this dipolar interaction by essentially developing a magic wavelength trap that allows us to control these AC start fits. And then show you how we can use that to entangle a pair of molecules in tweezers, and then time permitting, I'll tell you a little bit about how this extends to lattices. Okay. So actually, I have 3 experiments working with rubidium cesium. The oldest one, actually, we first made molecules a long time ago, 12 years ago now. And really, this has been the workhorse where we learn how to control the molecule and learn about all of its internal structure. And so what I will show you, although I won't acknowledge it very often, draws on that decade of research in terms of understanding the molecule in this experiment. But mostly I will focus on these 2 new experiments. Let me first tell you about how we make the molecules, because it's important to understand how we can manipulate and detect them. So this is now a fairly standard procedure. So the challenge is really to take a pair of atoms, rubidium cesium, of course, in our case, and transfer them to this absolute ground state of the bound dimer, which is bound by about 4,000 wave numbers, or 120 terahertz or so. And the way we do this is we've heard about Feshbach resonances already. The first step is to form a weakly bound molecule by sweeping across a Feshbach resonance. We do this actually at 197 Gauss. This is the bound states near threshold. So this binding energy is in megahertz. So this is bound by 2 megahertz. So this is an incredibly weakly bound molecule compared to this ground state. And we sweep across this resonance, follow this bound state down to here, around 180 Gauss, where we can then transfer it to the ground state. And we do so optically using stimulated Raman adiabatic passage. So this 2-pulse scheme drives us down to the ground state. You see the Feshbach molecule number disappear. And then we always break the molecule apart at the end of the sequence by reversing this Dirac pulses and recover the atoms that were a molecule. This is important. We don't have a cycling transition in rubidium cesium, so we can't scatter photons to detect the molecule directly. We always break it apart. This works really well. Actually, we've almost achieved 99% on the transfer now. And crucially, it goes to the absolute ground state of the molecule. So on the previous slide, I mentioned that molecules have hyperfine structure. And so this is the hyperfine structure of the ground state of rubidium cesium. There's actually 32 hyperfine states associated with nuclear spins. So although the rotational quantum number is 0, we still have these 32 states, but we couple to this absolute lowest state. The next rotational state has 96 hyperfine states, but we can drive transitions up to this state using a microwave field, and the selection rules limit the number of accessible hyperfine states. Okay? So for the most part, you can forget about this hyperfine structure. It's something that we've had to learn how to deal with. It has advantages, you can use it, but I probably won't mention it. I'll just talk about the rotational degree of freedom from now on. Another point to emphasize is this return stirrup only addresses this state, and so it effectively gives us a state-sensitive detection. So we only detect population that remains in this state. And that's how we make and detect our molecules. So what does this look like in tweezers? So you're probably familiar with tweezers. So we take a large high numerical aperture lens, we focus down several different colors of light into a laser-cooled sample of rubidium and cesium. And this allows us to trap single atoms. And we detect the presence of single atoms by detecting the fluorescence using the same lens, and put that onto a camera. And then you can construct these histograms where the presence of an atom, cesium or rubidium, is well distinguished from the absence of an atom where the counts are much lower. So this is how you can detect single atoms in the system. The thing that you do when you start an experiment like this is build your local landmark. And so if you ever come to the northeast of England, this is a sculpture, the Angel of the North. It sits just south of Newcastle, and then this is our rendition in cesium atoms. So these established techniques of using spatial light modulators and AODs allow you to position and arrange these atoms into these arbitrary patterns. So the tweezer experiment proceeds like this. We load rubidium and cesium selectively into different wavelength traps. We then do Raman sideband cooling. It's important to get them all the way to the motional ground state of their respective traps. And Thomas will probably remember this paper from a very long time ago, which shows that in order to actually couple into the ground state, couple the atoms into the molecular state, you have to be in the ground state of relative motion in the trap. And so you see if you sweep the scattering length, it's only this lowest motional state that couples into the molecular state. So that's why we have to do this very good cooling to the 3D motional ground state. We then very carefully merge these two traps. We move the 817 tweezer to overlap with the 1065 tweezer, and then ramp one off, and that leaves a pair of atoms as shown here in single tweezers. And then we do the molecule formation that I told you about. This doesn't work everywhere because our cooling is not perfect. But where it does work, we get a molecule, and where it doesn't, there's still an atom pair remaining. We can use the fact that the atom pair remains to detect the error. Actually, we can turn on this 817 tweezer and pull out a rubidium atom and use this as an error flag. It shows where the molecule was not formed. We then do our experiment, and at the end, we always break the molecule apart and separate the atoms and post-select on recovering the atom pair, ignoring those sites where we have the error flag. Okay. So this is just, let me jump ahead. This just shows you the kind of error budget. I'll not go through the details other than to say that basically when we prepare an atom pair in the correct states, then our probability of forming a molecule is somewhere between 40 and 50% in that tweezer. But crucially, this molecule has a very high occupancy in the motional ground state. So we're actually preparing the molecule in a single motional quantum state and a single internal state. And this efficiency is totally limited by how well we can cool to the 3D ground state in the tweezers with Raman sideband. So then we can play with the molecule, okay? So we can drive microwave transitions. So this is Rabi oscillations on this n equals 0 to 1 transition. We can see the different hyperfine states. We can go up the ladder, we can go up to n equals 2, we can go up to n equals 3. Ardash will show you that we can go up to n equals 8. It's really just limited by the microwave hardware that we have in the experiment. Okay. And this all builds upon the fact that we've analyzed this molecule in depth. And so we really have a fingerprint of these energy levels that we can just dial in microwave frequency. One of the really powerful and important techniques is we can do multi-state detection in the tweezers. So imagine we have two molecules, n equals 0 and n equals 1. If we break the molecule apart in n equals 0 with the stirrat, that doesn't touch the n equal 1 molecule. Remember, it's state sensitive. And so we can then pull out the rubidium atom into a particular line of tweezers, leaving this molecule in place. We do a pi pulse on that molecule, break it apart, and then pull it out into a different, pull the rubidium atom out into a different tweezer array. So in that way, we map the state of the molecule onto the position of the atoms and get a state sensitive readout. So this is now driving Rabi oscillations, but detecting both states. So you can see here, the molecule is n equals 0, the rubidium atom appears in the n equals 0 trap, and over here, the molecule is in n equals 1, and the rubidium atom is detected somewhere else. And this mitigates a lot of errors that otherwise would contaminate the measurement. Okay, so that's the tweezer platform and how we can control and manipulate individual molecules. I want to now address this challenge of actually getting long coherence times on the rotational transition. Okay. This is something else that we measured in our bulk gas experiment with this apparatus. And the results were like this, and this is actually one of my favorite plots. So I want to talk you through it. So what you're looking at here is the microwave transition frequency. So this is at 980 megahertz, remember, for rubidium cesium, up to all of these hyperfine states in n equals 1. The color indicates where we're able to drive a transition. So red and blue are transitions of different microwave polarizations. Yellows are states that are inaccessible because of the selection. And then what we show in this plot is that transition frequency as we vary the intensity. And each dot is a spectroscopic measurement, and the lines are the theory. So the good news is we completely understand this. This is for the laser polarized perpendicular to the quantization axis. You get a different pattern for parallel. Actually, you get a different pattern for every angle in between. Okay? The bad news is wherever you look, there's a strong intensity dependence to this transition. And this is the problem. These are tensor light shifts that really limit the coherence in the molecular gas. So if you imagine molecules sampling different intensities, when you try and drive this transition or put the molecules in a superposition, they then oscillate at different frequencies and rapidly dephase because of these light shifts. These arise from, actually, I think the same anisotropic polarizability that Dan is interested in at some level. In the molecule, it's the fact that actually the polarizability along the internuclear axis is different from the value perpendicular to the internuclear axis. So we can write this as an isotropic polarizability, which is just their average, and an anisotropic polarizability, which has an angle dependence and is proportional to the difference between these two components. This is actually negligible in the ground state, but in the first rotationally excited state, it mixes the MN projections and therefore mixes MF and leads to this beautiful pattern of state and avoided crossing. And you can see that looking at the matrix elements of this interaction, it has both diagonal terms, but also off diagonal terms. And they all depend on this polarization angle beta. And it's all proportional to alpha 2. I want you to remember that because we're going to try and make alpha 2 0. It's the way to get rid of this. And just to emphasize, this is a problem which is common to all molecules. And so if you look into the field, you'll find lots of inventive tricks to try and combat this. But typically it would limit coherence times without some dynamic decoupling to 10 to 100 milliseconds or so. So we had a very fruitful collaboration with Svetlana, And she pointed out that we should be able to make a magic trap. And that's the understanding of that comes from the fact that these polarizabilities come from very different sets of transitions in the molecule. And so by tuning the laser in the vicinity of one of those transitions, you can control one of the polarizabilities without altering the other. And the transition we use is this X to B transition, which is normally forbidden, but has some weak mixing with this A state. And that allows us to control alpha parallel without affecting alpha perp. And so effectively, we can tune alpha parallel to a value where this alpha 2 goes to 0. This problem goes away, and we should have long coherence time. That's shown here in theory. So here we're scanning the laser detuning between these two vibrational levels. In the vicinity of the vibrational transition, the transition to this vibrational level, you get a pole, of course, but the pole is only in alpha parallel. It doesn't affect alpha perp. And so at this point here, which I zoom into here, then the polarizabilities of n equals 0 and n equals 1 become identical. And we get this magic condition where the two potentials associated with the trap in the molecule is experiencing in n equals 0 and n equals 1 look identical. And the dephasing goes away. So this is the magic condition. If you're a little bit worried about tuning close to a transition, don't be. These are narrow line transitions. Their width's only 14 kilohertz, and we're detuned by 186 gigahertz. So actually far detuned from transition. We can zoom in and optimize this magic wavelength doing a Ramsey sequence. We do a standard Ramsey sequence and look at the contrast and then vary the tuning of the laser to map out where the contrast is the greatest. That's shown here. So this is the contrast from the Ramsey sequence as a function of the laser detuning. The different curves are actually for different superpositions in the molecule. So for example, this red is 0 and 1 labeled here. And the green is 1 and 2, this case here. You'll see why we use different transitions in a moment. So the magic wavelengths, of course, are where these peak. They do vary ever so slightly. We understand why, and I can tell you about that in a break if you're interested. But essentially, for any pair of states, we can dial the wavelength of the trap to be exactly magic. So let's look at how good this is. So let's first of all look at this 0 to 2 superposition. Okay. And straight away, we measured a coherence time of about 0.8 seconds, which was, compared to our previous measurements, is perhaps 1,000 times better than we'd ever achieved in rubidium season. And then with just a simple pi pulse, we see no loss of coherence over this 0.7 second measurement time. So this is great. The good news is it should be long enough to see dipolar interaction. And so we can now go to a superposition of 0 and 1, and this corresponds to actually creating a gas of rotating dipoles in this superposition. And of course, these dipoles interact, and they interact randomly because I've got a thermal gas of particles moving around in this bulk gas experiment. And so it leads to additional dephasing. So we see a shorter coherence time, but this time it's good because it's due to bipolar interaction. And we can convince you of that by changing the superposition, which changes the effective dipole moment, and see that the coherence time drops for the larger and larger dipolar interactions. And you plot it the correct way, you get a straight line. It's just 1 over the dipolar interactions. Okay. So this came about 10 years after starting to work with molecules, and shows how hard it is really to unlock this strong dipolar interaction in these systems, but really now proves that we can. The obvious question is that what happens if you go back to the tweezers? So we did that. It was a little bit of work because this lens was not designed for this wavelength, 1145 nanometers, and so we had to really cobble it in through the imaging path. And the upshot is we don't make very small tweezers. I mean, the foci are about almost 2 microns for this wavelength. But we can do really nice spectroscopy. So this is again measuring the Stark shift, AC Stark shifts in the molecule by doing a Ramsey sequence. and extracting the energy shift. So this is now measured in hertz with respect to this 980 megahertz. And we do that for different intensities. That's the different colors and also different detunings. And clearly this is the magic point. And the same data can be plotted as a function of intensity, just to show that this detuning, the frequency is really independent of intensity. Okay. All of these fit to a single number, and actually the takeaway message is for reasonable track parameters that we have in the experiment, and the coherence time associated with the trap should be about a minute. Okay. So this really shows that we've completely eliminated this differential AC start shift problem in the optical. We can try to measure that. For those of you who know how tweezer experiments work, you don't want to measure for a minute. So we've measured for 2 seconds, which was about the limit. And so this is a Ramsey sequence now measuring superposition coherence in rotational states for 2 seconds. Neither of the traps, there are 2 traps here, one red and one blue, neither are exactly magic, and they're detuned a little bit. But even in this case, we see full contrast fringes. Note, we measure a 6 hertz difference in the transition frequency for these 2 frequencies. Why do I have 2 frequencies? Because these traps are generated with an AOD, so they have to have different frequencies. And this 6 hertz difference will be important. Okay, well, first of all, we have to get rid of it. Let's see. So now we're in a position, we've got long rotational coherence on individual molecules. We should be able to control this dipolar interaction by bringing the molecules together and use it to entangle them. And so the picture is like this. We have this inherent spin exchange interaction. So when I have 2 molecules close together, actually these states should split into their symmetric and anti-symmetric superpositions, split by this interaction energy. Now, the fact that our tweezers are big means we can't get them very close together. So as advertised, strong interactions in molecules translates to about 6 hertz or so in this experiment, which in molecules translates to about 6 hertz or so in this experiment, which is exactly the size of the energy shift I told you about. So we have to do a little bit of work to make both tweezers magic. We do so with a complicated scheme where we chop frequencies and intensities. I can explain in more detail afterwards if you're interested. But effectively, we can make 2 tweezers magic. So this is now data from 2 separate tweezers, but only 1 molecule present. And it's just showing that within I think it's 100 millihertz or so, this transition at 980 megahertz is exactly the same. And we do the measurement with a pair of molecules, and we see the interaction shift. So now when we drive population out of down-down, where they start, there we populate these 2 down, up, and up, down equally, and we see the shift of half the interaction, so 2.6 hertz in this case. And of course, you can sit here and drive Rabi oscillations, and you get a collective excitation of a pair of molecules and see the route to enhancement that comes from that. And we can use this to then do entanglement. The simplest way, fastest way is actually to do the Ramsey sequence. So just do 2 pi by 2 pulses. During this time, the molecules are interacting through the spin exchange. And the output of this is oscillations between down, down, and up, up as a function of this time. So that's what we do. And we see that indeed we start and we see these oscillations between up, up, and down, down, with very little population being transferred into this sector. And then to produce a Bell state, you simply stop this at the correct time, which in our case is an enormous 86 milliseconds. And that produces this entangled state. We can quantify the entanglement, how good it is, by doing an additional rotation around an arbitrary axis and constructing this parity operator. And that should oscillate. It does, and the coherence of that gives you part of the answer. You can combine that with the measured populations at this point to construct the overall fidelity. Actually, we get a very reasonable, almost 98% fidelity on entangling this pair of molecules. Okay. So just to highlight that this is not the only experiment that has done this. So there are two experiments using calcium fluoride molecules in Princeton and Harvard, and also around the same time as us in Kang Lee's group in using sodium cesium molecules with much higher interaction strengths. Here you see 700 hertz. But actually our fidelity surpasses these, and I think it's really because of this magic wavelength trapping that suppresses a lot of the problems with differential light shift. Okay, so I think I've got 5 minutes left. Good. I want to tell you about extending this, right? So this is very beautiful, I think. Control of two molecules, control of the interactions show that you can generate entanglement. Of course, the realm of quantum simulation is all about pushing into the many-body regime, and an obvious way to do that is to extend to optical lattice. And actually, Anna Maria, I think, was an author on this nice paper from a few years ago, almost a decade ago now. But it really sets out, I like this picture that really shows some of the possibilities of molecules in this domain. And so what they show is, you know, in the case of pinned molecules, the simplest case, you just pin them to the sites of a lattice. Then there's a lot of physics accessible that really stems from this models of quantum magnetism. Of course, we had a question about, you know, why just two levels? Well, don't go to more levels, and then you get new physics, even with the molecules just pinned. And so one of the things we're interested in is trying to access this spin-orbit coupling that Anna Maria proposed in this context. And of course, then the holy grail is really to push and let the molecules move around and rearrange themselves in response to the dipolar interaction. And there, the natural description of the system is a TJ model. So simulating this in these systems would be very interesting. And there's nice experiments coming out of Jun Yi's group, which is starting to probe the physics in this system. So about the same time we built the tweezer experiment, we started a lattice experiment, which is much more complicated. So this is the apparatus. I will not go through all the details. But just to point out that with our magic lattice, in this case, the interaction energy should go up to 280 hertz for nearest neighbor molecules. And so really we should have much stronger interactions, but the same kind of coherence times that we see in the tweezers. So we should be able to see many interactions in the lattice in this case. So how this works is actually we cool atoms in this chamber, and then we transport them with a moving lattice into this glass cell. One of the details I've kind of glossed over is rubidium and cesium don't really like to be together. And so we actually do this sequentially. Take the rubidium, put it in a trap, move it out of the way, bring in the cesium, put that in a trap. And then we actually cool the two gases completely separately and then merge them at the final step to make molecules. And so we can actually produce two BECs this way. So this is a BEC of rubidium and cesium separated by about 0.5 millimeter in this glass cell. And the reason for going to all this is, of course, to have this microscope objective just below. And so now we can actually image individual atoms in an optical lattice. And so we can image the rubidium or the cesium. This is an image. So these are analyzing very sparse clouds shown here. And then if you have a more fully occupied, you actually get a parity projection when you do this imaging. So you get roughly half occupancy of the lattice. But what we're most excited about is using this for molecules. And so we've started to do that. So we actually prepare thermal gas of molecules still in a dipole trap, but then use this microscope for imaging. And the way that works is we have this gas of molecules, we pin them with the optical lattice, we break the molecule apart, and then we rapidly remove one of the atoms, and then we take an image. And the pictures look like this, okay? And so these are pictures of a cloud of rubidium cesium molecules where it's either been mapped onto the cesium atom or onto the rubidium atom. And each little dot is a single molecule. And If you want to know why I'm excited about this, because for 10 years, we've been looking at these little smudges of optical depth that we get from just a bulk image of the gas. So now we have this full number resolved imaging of individual molecules. We can actually go further than that. We can actually map the state of the molecule onto the species in a sequence that I don't have time to explain, but essentially n equals 0 becomes a rubidium atom, and n equals 1 becomes a cesium atom. So then we can take 3 images in the experiment, image rubidium, image cesium, then as a sanity check, we image both, just to make sure nothing has moved. And in this way, we're able to reconstruct the spin distribution of the gas and molecules in a single iteration of the experiment. Good, I'm almost done. And of course, with a microscope, you can also address, okay? And so we can prepare an impurity gas of n equals 0 molecules in this gas of n equals 1. And of course, you could then look at spin transport and so on with this state resolved detection. So there's a lot I think we can do. Still a lot to work on, but I think this is heading in the direction of being able to simulate some interesting physics. Good, so this is the summary. I've told you about the development of this magic wavelength trap, which we can combine with optical tweezers to give this really beautifully controlled entanglement of a pair of molecules. And then as the outlook, I mentioned our work on tweezers. There are some other topics that I don't have time to tell you about, in particular one about combining Rydberg atoms and molecules, where we have some interesting results. So let's talk about that during the week. And let me jump ahead across all the exciting preliminary things to just thank the group, in particular Dan and Jonathan, who lead the tweezer and microscope experiments. And as this picture is here, I just thought I'd highlight how beautiful Durham is. If ever you're in the UK and want to visit, please do get in touch. Okay. So thank you very much.
Thank you, Simon, for the very, very nice talk. We are open for questions. Maybe I can start. When you look at the dipole-dipole interactions in the trap, is the geometry 2D or what is the geometry?
For the bulk gas,
yes,
it's really a bulk gas. It's 3D.
3D. Okay.
Yes.
Okay.
Yeah.
So you do have chemical reactions.
Yes, we do. We have loss and all sorts. Yes.
Okay.
But,
I see.
Yes, we would like to go 2D.
I see.
But as you know, it's not so easy.
Yes. Yes.
Yeah.
Can you study Bose-Einstein condensation with this molecule? Is possible?
I think
what is the manageable equation in this condensed state?
so. I think it will be hard with the rubidium cesium because even in our bulk gas experiment, we don't produce very many. Well, so what I was going to say, we're building a new experiment. So maybe, I don't know if you know, I mean, BECs have been produced in both sodium cesium molecules and sodium rubidium molecules. And really the key to that is to be able to shield the collisions. I didn't talk about collisions here, but there are lossy collisions between the molecules. And there's a technique called microwave shielding, where you essentially dress the states with microwaves. And this prevents the molecules from reaching short range and actually stops these collisions. And that's how you can make a BEC. And then the question about the equation, I think this is really an open question. I think this is people are working on this because what you actually have is this really hard repulsive core associated with the microwave shielding. And I think it's not obvious to me whether like the GP formalism is correct. It probably needs to be changed. And so I think this is one of the exciting areas to be studied in the coming years. Yeah.
More questions? If I don't see more questions, let's time. Our next speaker, Sadiq.